Hi, this is Mrs. Bustamante. Today we're going to talk about the ideal gas law. And quickly, I'm just going to mention the ideal gas law only works on ideal gases. We're going to talk more about what makes an ideal gas here in a little bit, but just keep that in mind as we're discussing this. So the ideal gas law tells us that PV equals nRT. A way I like to remember it is PIV-NERT. Get it? PIV-NERT. So P stands for pressure, V stands for volume, N stands for number of moles, which is something new, which kind of differentiates the ideal gas law from the other gas laws we talk about. R, which is a constant, and T stands for temperature. Now, when you do the ideal gas law, you need to pay extra close attention to what units you're using because that determines which R value or which constant you're going to use. And then your other units should match that R value. So what's R? R is just a number that we're always going to use. It's defined by the molar volume of a gas at STP, standard in temperature and pressure. And if you remember back, right, we were talking about 1 mole of a gas at standard temperature and pressure equals 22.4 liters. So in my class, we're always going to be working with ideal gases. And so we can always use the ideal gas law, but we will talk about what makes a gas not ideal, if you will. So what's the difference and how do you know which R value to use? Well, pressure, we've been using lots of different values of pressure. Pressure, if you're using the ideal gas law, you either need to use kilopascals or atmospheres. And why is that? Well, we have two different R values that we know. We can say the RR constant is equal to 8.31 kilopascals times liters divided by mole times Kelvin. Or we know that R is equal to 0.0821 atmospheres times liters divided by mole times Kelvin. So we can either work with kilopascals or atmospheres, and we need to make sure that we match this to our pressure value, whatever units our pressure are in. Volume needs to be in liters because that's what our constant will give us, uses the units in. And now we can deal with moles, so we can find out how many moles of a gas we might have. And as always, all unit long, we need to keep working with temperature in Kelvin. Now you might ask, why do these R values have such complicated units, right? Well, it's really because it's a constant and then we can cancel out the other units in our equation. So we end up just with what we are looking for, if you will, or what the unknown is. So here's an example problem. When filling a weather balloon with gas, you have to consider that the gas will expand greatly as it rises and the pressure decreases. So the gas expands as the pressure decreases. Let's say you put about 10 moles of helium gas into a balloon that can inflate to hold 5,000 liters. Currently, the balloon is not full because of the high pressure on the ground. What is the pressure when the balloon rises to a point where the temperature is negative 10 degrees Celsius and the balloon has completely filled with gas? So what's a clue to you that you should be using ideal gas law? Anything that asks for moles. It's the only equation that uses moles, so that's kind of your giveaway. And that's my giveaway in this problem, that I need to use ideal gas law. They tell me I have 10 moles of my helium gas. They tell me that the volume it can inflate to is 5,000 liters, and they want to know what is the pressure going to be when the temperature is negative 10 Celsius. Of course, I can't work in Celsius, so I add 273 to get it into Kelvin, which is 263 Kelvin, and then I'm going to choose the R value that's 8.31 kilopascals times liters divided by mole times Kelvin. Now, could I have used the other R value? Sure, they didn't specify what they wanted my answer in, what type of units they wanted my answer in. So it would have been okay because I'm solving for pressure either way, but you would get a different answer. So I'm looking for my pressure, and I'm going to use PIV-NERT, PV equals nRT. And another thing to remember about these is there's not necessarily a before and after. We just have one volume, one temperature, one pressure. So I go ahead and plug in P times 5,000 equals 10 moles times 8.31 kilopascals times liters divided by mole times Kelvin times 263 Kelvin. So I'm just going to talk about units here for a second. I'm going to take Kelvin divided by Kelvin, so that's 1, and they'll go away. And I'm going to take mole divided by mole, which gives me 1, so that will go away. And when I do my math here, when I multiply these three numbers together, I get 21,855.3, and I'm left with kilopascals times liters. And on my left side, I have my pressure times 5,000 liters. To get P by itself, I divide by 5,000 liters. And my golden rule tells me if you do unto one side, you must do unto the other. So I divide 5,000 liters on the other side. Liters divided by liters gives me 1. I do my math, and I get 4.37 kilopascals as my answer to this problem. And that's your first ideal gas law problem. So what makes a gas ideal? Well, the ideal gas laws only work on ideal gases. What makes them? We say that ideal gases, the particles in them take up no space. We say that there are no intermolecular attractive forces, so one molecule isn't attracted to another in it. They're in constant random motion, and they have perfectly elastic collisions or no kinetic energy change. In this class, we're going to say all the gases we work with are ideal, and they fulfill these requirements. But you should know what makes a gas not ideal, because not all gases are ideal. And most of the time, however, gases will behave ideally under a wide range of temperature and pressure, but there are a couple instances where they don't. If you have a really high pressure, you start to see intermolecular forces take place. They start being attracted to each other. Or if you have a really low temperature, they start becoming liquid, they start moving slower, and they're going to start to stick together. Large particles, particularly polar ones, will become attracted to each other, and those intermolecular forces increase, and they would also not be an ideal gas, and they would not follow this rule. But again, for us, we're going to use all our gases to be ideal.